I'm sorry, it's muted.
You just make it, you define the transmit covariance matrix WK. You could assume for now that it can be, it's a rank 1 matrix, right? So if you multiply the beamformer by its permission, you get the rank 1 matrix WK. And then the beamformer power 2 norm square of the beamformer is equivalent to the trace of the rank 1 matrix. And also you can represent the outer product of channel vectors as a rank 1 matrix, capital HK. And now plugging this into the previous formulas, you get this equivalent representation, minimizing the power, equivalent to this one. Trace of WKHK is basically equivalent to plugging in those expressions there. WK, remission, HK, remission. This is equivalent inside the trace. You can move terms around. The same as trace of WK remission, HK remission, WK. This is a scalar, right? So you can remove trace, and this is equivalent to WK remission HK square, which is equivalent to HK remission WK square, right? Similarly, for all these other terms, and you get the SI constant, right? You can add here equality, right? So because this is a linear. Now this is a linear expression, linear constraint, so you can add here equality here. The only problem here is that we assume this WK to be rank 1, and if we impose this as a constraint, cannot be solved. Right? But the straightforward trick that is applied often in this type of problems is to relax this rank constraint just by assuming the rank of WK can be anything between 0 and the size of the matrix, right? So this one here, this is equivalent to saying that the eigenvalues of this matrix are positive. Right? Here, obviously, we have only one eigenvalue. Mm-hmm. But here we can have up to the size of this matrix, which is S of t. So this is called semi-definite relaxation of this rank 1 constraint, and this is a semi-definite program, and it can be solved. Now it can be shown, and it's quite intuitive that since we have an SOCP solution, it's optimal to the convex problem. The rank, when you solve this, the rank of WK will be always 1. So you can simply use eigenvalue decomposition to fit the only non-zero eigenvector, and assign it to be WK multiplied by the eigen.
Why the rank is always 1?
There's some formal proof in the, I don't remember the exact steps for the proofs, but it can be proved. If you want, I can figure out that and show it next time. It's not important. You can find it. The SOCP is optimal, right? Let's say you would not benefit anything. Maybe the first intuition, you would not benefit anything by assigning larger rank here than 1, since we have our optimum solution
With rank 1.
with rank 1. Maybe that's good enough for now. Okay, then we can look into, of course, these are nice, and for small size problems, we can solve these quite efficiently, right, with CVX. Or you can even write your dedicated solver using Newton method, if you like. But there are alternative solutions, maybe in the, well, if you write your own solver, that's possibly always the best thing to do. But if you want to use simple matrix manipulations, and you can see actually that the problem structure is fairly simple. We have a SINR, like coupled, the SINR, fixed SINR target for each user. These are the only constraints. We have just capital K constraints, and there are no constraints that basically, there's no power constraint that could couple across multiple users. Of course, the beamformers are coupling. The beamformers are appearing in every user, so beamformers are coupled. Okay, so we can start writing the Lagrangian. Okay, so we just take this expression, maybe the this reformulation of the SINR constraint, the objective. So the Lagrangian is simply the objective minus the sum over all constraints is assigned with corresponding dual variable, right? And then we just start reformulating it. You can see that lambda appears in each term here. You can pick the n0 out, if it doesn't depend on the beamformer, and then you can rearrange these terms such that you have the a matrix inside multiplied by the beamformer WK from both sides, summing over all K. You can do the math, and you will see that these two are equal. It's just rearranging these terms. Okay, so if you want to write a dual problem, basically, we want to find now what are the optimal dual variables. The first step after Lagrangian is to write the dual function. The dual function is taking the infimum over the primal variable WK. From this expression, you can see that this would, if this matrix is has a negative eigenvalue, right? We can find beamformers that basically push this function to minus infinity, right? This is not interesting. So the only possibility to have a positive, meaningful result for this infimum is to constrain this matrix to be positive semi-definite, right? The eigenvalues should be positive, right? In that case, we can find minimizing W is basically making this term to 0, right? And then we have left this term here. So this is the only, let's say, solution that makes is useful, right? Because it's minus infinity otherwise. So basically, the dual function lambda k 0 only if this matrix here is positive semi-definite. And this matrix now depends on this lambdas, right? Depends on what you assign to lambdas. You have either PST or a negative matrix, right? So this PST matrix now constrains this feasible lambdas. And that's what is next. From the dual function, you can write a dual problem with the objective. Now we have the constraint from the physically condition. And obviously the dual variables by default have to be positive. Right? So we have now another SDP, right? SDP, we have a linear objective scalar variable, but we have semi-definite. So this matrix, semi-definite matrix, right? So we have semi-definite problem. So solving lambda k from this gives you the optimal dual variables, and then this holds the sum of dual variables multiplied by the noise has to be equal to the primal solution. So far so good. Of course, this doesn't help. Of course, we can solve these W's directly from the SOCP or SPP. But now, if we have an expression, we can go back to the Lagrangian. Optimality conditions state that at the optimal solution, the derivative differentiating the Lagrangian with respect to lambda and W, or the primal variable W, should vanish at the optimal, right? So we differentiate the Lagrangian with respect to W, because this appears here, and what we have left, we can differentiate from left or right. What we have left is, if we differentiate from the left, we have this one here equal to 0, or this one equal to 0, right? Both are fine and lead to the same solution. So we can rearrange these terms to this equality here. You can see that now the WK happens to be both sides, right? Which in principle it's problematic because one solution for equality is to assign WK to be 0, right? Makes sense. What we can do is that we can just invert this both sides by the inverse, to multiply both sides from left by the inverse of this matrix, and we get an expression for WK, which is the inverse of the matrix. It's kind of regularized zero-closing matrix, right? We have a regularization rate. But these are kind of regularization rates. But we have an identity matrix, but we can also assume decently kind of appearing here. Well, we'll discuss about the actual regularized set of motion later on. Anyways, it includes the identity component and then rank 1 matrix multiplied by dual variable for each user. So you can actually already look this the importance of these lambda values. If the lambda values are high, right, for particular user, it means that we should that particular user will see very little interference from other users, right? After inverting, right? So we can, by changing these lambdas, we can shape how much interference is generated from one user to another, right? But there's a graphical illustration later on. We will come back to this. Okay, so now we have this complicated term left here. So you can see that now we have this kind of a match filter part matched to the user K channel and a scalar. Right? This is just a scalar. This is a scalar. Right? So we can call this constant, a CK. Okay. So now we have a B-former expression WK, it's an inverse the match filter front end and then the scale. But the scalar does not really matter here because if we want to find a normalized B-former, the scalar here vanishes, right? We can just remove it and then find a normalized beamformer, which is the unnormalized part without the scalar divided by the norm, okay, using 2 here, the normal, right? So this is now a normalized beamformer. You can call it UK, meaning that the true norm of UK is 1. Right? So if we have these optimal dual variables now from the dual problem, we can simply assign those dual variables here and then normalize it. We get a optimal beamforming direction, normalized direction. And what is left is just, since we have the SINR constraints, we have fixed SINR constraints. Now we have the optimized normalized beamformers UK. What is left is to find the optimal powers, right? And we have expression for that, and that was in 5.4. Okay. So when we have the U is fixed, we can compute the G matrix again. Is the coupling matrix between users. Zero forcing is the diagonal matrix. And then we have the fixed SINR, so we can compute this A, and we can compute the diagonal of A. We know everything here. By inverting both sides with this matrix, we get an expression of P. And then we have the optimum beamformer. Okay, so far so good. We have the beamformer structure, the optimum beamformer structure from the optimality conditions, right? It has this structure, normalized. This arbitrary constant does not really matter because it vanishes. We can add here C and add here C. We can multiply this by 1 million. It will cancel out, okay? Just to show that. The scalar, any scalar here does not matter for the normalized beamformer. So far, so good. Still, the lambda we had to solve from the SDP, which is still complicated, right? It's very simple STP because we are just finding k scalar values, but it's still an STP. So just to make more sense, practical sense, we should have a better way to find these lambda values. And that can be, again, seen directly from this expression. Now, we can multiply both sides. Here, we can multiply both sides by hk permission. Right? Still, we have equality, right? That's exactly what happens here. We have multiplied wk from left by hk permission and the wk expression by hk permission. Now you can see that these two terms appear both sides. So we can just, and these are scalars, that's complex value scalars. So we can just divide both sides with this value, right? So they disappear. Here we have 1 and 1, right? Now, from this expression, we can solve lambda, right? Lambda k is equivalent to 1 divided by this scalar and this scalar, right? Exactly like that. Now, when you look at this, of course, lambda k here. So the lambdas appear now in both ends, both sides. Lambda depends on lambda, right? So this type of expression suggests that, and you can show that this relation can be interpreted as standard function, standard interference function. You can Google standard function, standard interference function. If you have this type of a fixed point relation, you can, given that some conditions hold, you can show that you can start from any value of lambdas and just keep updating new lambdas based on old lambdas. It's guaranteed to converge, independent of the starting point. You can start from zeros, right? Or you can start from any value. It's guaranteed to converge very quickly to a fixed point solution, right?
So all the lambda case should be updated all together, or we update one, if converged, we go to other. How is it?
Doesn't matter.
I guess we should update all together, because if we fix one and change others again.
It doesn't matter. You can say you can do one user at a time.
Okay.
So you start from all zeros. You pick one user, lambda 1, right? You have t plus 1. These are all zeros. Okay. What you get is just like a match filter, like noise-free scenario or interference-free scenario. You go to second user. That first user appears there. Right. Actually, it has better, I would say. I mean, you can do both. But maybe you can check. This is actually, you should implement this in one of your homeworks. So now this has actually, in slide set 4, when we discussed about uplink downlink duality, we had similar solution for the uplink, dual uplink power. Right? So actually, we can rewrite this a bit differently. So this SI in a constraint, where did I start from? the uppermost equation that can be also equivalently written as I plus I not equal to k lambda I hi permission wk equals 1 over gamma target lambda k hk permission wk. Just removing the home term from here, right? Both sides. Removing the term wk, removing the term lambda k hk permission wk from both sides, right? We have equality. Okay. Now, if we now plug that in there, well, that follows. And if we write the plug in the equivalent informal matrix vector from this formulation in 5 of 18, what we get is hk permission wk hk permission I plus I not equal to k hi permission hk lambda k 1 over gamma target hk permission wk. Again, these cancel each other. We have 1 here. Now we get an expression lambda k is gamma target divided by hk okay. So now we are actually quite close to, okay, this is again a 6-point iteration, so we can add here I plus 1, I. So this is equivalent, right? No difference. The only difference is that now for practical implementation, if you want to, like you said, if you want to update all users at once, we don't have to invert this every time when we update lambda. It's just invert this because it's the same for all users, right? This inverse here is the same for all users, so we can just invert it once. Here, the inversion is user specific, right? Because that particular user k is missing. Okay, so from the implementation perspective, this might be easier. Okay, but anyways, just to show that we have this slide set 4. The dual uplink, the optimal solution for the dual uplink powers right here. You can see that they are almost equivalent, right? Lambdas are related to q's, and this is actually something very interesting. So here you can see that if you can interpret this as in the dual uplink that you have when you add qk here, this becomes the SINR at the output of the MMSC. Right, qk of that is here. So you can update qk based on these instantaneous ratios of SINR target versus the actual SINR for given dual uplink powers. Meaning that if the actual SINR for this given Qs is smaller than target, increase qk with that ratio. Right? There's another interpretation of this point. Okay. The similar interpretation can be done for this Lagrange duality formulation. Here. Now we can see that if we now assign lambda k to be qk over n0, we plug in qk over n0 here, qk over n0 here, and then qi over n0 here. Now we can take n0. We can take 1 over n0 out. We have identity here plus qi, hi addition. Okay, and then this 1 over n0 goes in front, right? Cancel. And this cancels. Okay, so we have equivalence here. So this is a nice interpretation that now this dual uplink downlink duality, the power duality, the Lagrange duality are fully connected, right? By assigning lambda k to be qk over n0, we have the exact match, right? So these dual values can be interpreted as noise normalized dual uplink powers. So we have also, of course, when you look at the primal dual, the duality gap has to be 0, meaning that sum of lambda k and 0 equals W sum over, okay, this equals sum over pk, and this equals, of course, qk over n0 times n0 equals sum over qk, right? So the sum power in downlink and dual uplink both. Okay, this is just to give you some connection between the uplink downlink duality approach that we discussed earlier and the Lagrange duality. So now we have a way to compute, like very quick and easy way to compute the optimum beamformers. What you start is you have your optimization problem. You have downlink. You want to serve multiple Antenna users in downlink. You have a certain SINR target for each user. They can be different, right? It can be anything, arbitrary constraints. You get these SINR constraints, you get the channels, right? Plug them in here and iterate, get this Lagrange multipliers lambda k. Okay, these are the optimal optimal dual variables. Then you plug them in here. You get the normalized beamformer, UK for each user. Then you go to 5.4, solve optimal PK square root. Square root of PK times UK is your optimum downlink beamformer. Okay.
It would be if we use 5.4, would it be different? Powers would power be different than this here? If, for example, when lambda k is found, you just assign PK to be n0 lambda k. Would they be different?
Can you repeat?
We iteratively find lambda k, right? When
Yes.
it converges. Then we assign PK to be n0 lambda k.
QK over N0.
Yeah, QK we. Oh, okay.
These are equivalent. If you plug in here QK over N0.
No, not QK. I was talking about PK. If you consider PK to be n0.
No, you cannot plug in PK here, right?
Mm-hmm.
The beamformer structure depends only on these lambdas.
Mm-hmm.
Lambdas control how much interference you allow between different users. PK is just then the power allocation to meet the SI napons. They are connected, but not directly. You cannot assign PKs here. Right? Mm-hmm. In uplink, powers are fixed when you compute the uplink to receiver. Here we are computing the transmit beamformer. Mm-hmm. Right? Okay, we will actually get back to the relation between the transmit and receive beamformer when we discuss about heuristic solutions. Okay, now we have this optimum lambdas from the fixed point iteration. We can write it as a diagonal of lambdas. So this summation here, we can write in a matrix form, H diagonal lambda matrix H Hermitian, where H is just a stacked matrix of user-specific channel vectors. You just stack these capital K channels into one matrix. So now the inverse is just replace this term with the matrix multiplication. And recall that the user-specific beamformer depends on the match filter matched to that particular user K, right? The match filter form. So if you think and this is the column vector, this is a column vector. This is the same for all users, right? So you can stack these transmit beamformers W1, 2, 3, 4 also just by stacking these channel matrices, channel vectors into channel matrix, right? And that's exactly what follows here. You're stacking W1 to WK. Here you have H1 to H capital K. Okay. So here each column corresponds to user-specific transmit beamformer. And then we have a diagonal power loading matrix, which looks a bit complicated because now it consists of the normalization, right? It's basically this term here. This is a scalar for user K. Okay. So then you just multiply a matrix with a diagonal matrix of these scalars, right? And then you get the WK. So maybe you need to do the math yourself. This is just a diagonal matrix of these scalar values. It's given here. T1, divided by the norm of the vector 1, the normalization factor, and the last diagonal term theta capital K divided by the normalization factor, right? So here we have, this is now equivalent to, as computing this W here is equivalent to computing W1 to WK separately and stacking them into the matrix, right? It's equivalent to computing this matrix directly. Okay. Be clear? But yeah, you can play with MATLAB if it's not clear at first sight. Okay, now we can look into a bit more details about the structure of this beamformer. You can see that there is this identity regularization term here. What happens? So we can look at these two regimes when we have low SNR, so transmit power is very low, or high SNR, transmit power is very high, meaning that the SNR constraints are high. They are related. So, using again this primal, the duality gap, primal dual equivalence, the objective of primal problem should be same as the objective of the dual problem. Just divided both sides with N0. So you can interpret this as an SNR, right? Power divided by the noise. This is the total transmission now. Equals now sum of lambdas. And now this total transmit SNR goes to 0. That's when the SNR goes to, that's like the asymptotic result when the SNR is very low, meaning that also the lambdas go to 0. Okay. When we plug in 0 lambdas here, this term here cancels out, and we have just identity here. So we have match filter left. Again, the match filter is the optimal in the lowest end, just like in the uplink. Let us look at the MMSC receiver. Then you say, okay. Now at the highest NR, the sum of lambdas goes to infinity. First, just before, just to see, just to be able to manipulate this, we apply for this matrix here. We apply this equivalence. I plus AB inverse times A is equivalent to A times I plus BA inverse. Okay. This holds over. So here, this we assign the A goes in here, and we reverse. Right, so this one here we assign to be B, which is A. We get lambda H times H. Lambda goes to infinity. This term here can be discarded. Okay. Now we have a inverse of lambda times this matrix. So we can use another inversion rule. If we have A, B, inverse, these are square matrices. We have the inverse, A inverse, holds for square matrices, right? And this is invertible because we assume that here we assume that K is smaller or equal to n sub t. right? So H is a Hall matrix, right? N sub T times K. Now H Hermitian is K times N sub T. So this is K by K matrix. Okay, so it's always invertible. Then K is smaller than N sub T, and HK are not linearly dependent. Okay, so we can take this lambda outside. This is the diagonal scaling here, and we have zero inverse, zero false. Okay.
Sorry, what is P tilde?
P tilde. That is P tilde. Good question. Why did I have tilde there? Yeah.
Because I guess you also consider ignore I in the P.
Not yet here.
No.
Maybe this is too early.
P are regularized, like maybe you are also ignoring I in the regularized P.
Maybe. Yeah. Anyways, you can compute those, right? You just apply the 5.4 formula and you get this. Normalize again. Right. Because this is the normalization. Okay. Well, it doesn't matter. It should, because P includes this normalization, right? Here, if lambda goes large, it still holds.
I is ignored, it's almost the same.
It is, but okay. It holds in asymptotically. Okay, maybe that's the reason. But also this holds only asymptotically. So this should be also P tilde then, right?
Yeah.
Okay. Good point. Something like that. Maybe it's just an approximation. But you can always redefine. Okay, I think the P tilde should be here as well.
Not tilde, maybe hat, because they.
They are not the same. Certain. Yeah, P hat, P tilde. Okay. But the same thing is just to. Okay, yeah. You have a new definition without this identity here, and yeah, basically that's normalizing by the channel for the other case. So this is the graphical interpretation. Again, in the lowest NR, the beamformer is matched with the channel direction. It's aligned. It's just that your transient beamformer is just that complex conjugate. The Hermitian transpose of your estimated channel with proper power loading, of course. This is actually something you're also asked to study in your homework. What happens if you apply match filter for larger range of SNR? And then in the other extreme, the beamformer becomes just a projection. You project the beamformer to the null space of the subspace consisting of all whole user channels. Okay. All right, let's take a break here. 5 minutes and get back 15 past. Okay, now we have this optimal beamformer structure for minimum power beamforming. So this is actually one of the few problems that can be solved optimally. But we can guarantee that this is the local optimal. Another one is the max min SINR. This is your homework. because you can solve the maximum SINR via minimum power by bisection, right? You can assign an SINR for every user here, solve the beamformers, check the power, right? If that power is more than your budget, you decrease your SINR. So you can solve that via bisection, right? You keep searching for SINR level until you meet the power constraint. And for that, you can also claim optimality. That's your homework. Okay, but now in general, we will see actually that the beamformers in general have, for any optimization problem, we will see that the beamformers will have this structure. The dual variables, lambda, are changing, and the power allocation are changing depending on the actual objective. But the structure is always this. We will look a couple of other objectives later on. So, but before we go there, so we basically can just state that finding optimal lambda k for any objective is difficult in general, but most of the other objectives that can be considered in practice are non-convex. They require some approximations, iterated. There's another extra iteration loop for the approximation. So sometimes we just would like to use something simple, heuristic. One of them is to assign all dual variables to be equal. Lambda k equals lambda. Now it's much easier. You just search for one value instead of capital K values. Okay. So now if we now plug in this lambda k equals lambda to the earlier expression, and so this is the identity matrix times lambda, so we can take the lambda in front. So now we get the regularized zero-forcing expression. And you can write it in both ways using this I plus AB inverse times A equals A times I plus EA inverse. Right here. And now, again, applying primal dual sum property. So primal and dual should be the same. Okay, this is the general, which should be equivalent to P, is the transfer power. So now if we fix P, fix N0, and fix all these lambda to be equal, we can solve lambda from here. This is equal, lambdas are equal, then that one over there leads to K times lambda N0 equals P, therefore lambda, the optimal lambda is N0 K. Right? Now when we plug in this value, this kind of SNR per user, right? Assuming each user has the same power, plug that in here, you can see that we have exactly the same expression as in the uplink. Right? In the uplink, we have each user has P over K power. Right? This is the uplink MMS receiver with equal power per user. Okay, and this is the normalization. So this is the normalized MMSC receiver, uplink MMSC receiver. So we can call it transmit MMSE beamforming. So it's basically finding the optimum UK for this uplink SINR, right? UK is fixed here. Interference index is changing here. The channel index, right? So this is an uplink solution. So you can show that when you assign a single lambda, assign all these lambdas to be equal, use the primal dual property, solve lambda. From there, see that lambda is equivalent to kind of equally dividing the power between users in and that as a result that can be interpreted as equivalent to uplink MMSE receiver. So now we are using normalized uplink MMSE receiver as our transmit beamformer. That's why we call it transmit MMSE beamformer. It does not minimize the MMSE necessarily. It doesn't, depending on the power allocation, right? Does not necessarily minimize the downlink MMSE. We can still use this as a normalized beamformer and solve the minimum power problem, for example. We can plug that in 5.4 and solve powers. Powers would not be optimal because we are using suboptimal beamformer, but we can still use that normalized beamformer. That's actually one of your homeworks to study the performance.
But here still we need P, right? We are minimizing P.
And now, okay, that's a good point. Yes, good point. We are not. The P has to be fixed. Yes, so it doesn't work for minimum power beamform because we don't know the power beforehand. Okay. But for this, we can now if we have a fixed power budget, right? Then we can compute for that given fixed power budget P. We can compute this transmit MMSE beamforming. These are the normalized beams now, and then we can do power loading for whatever objective.
So it's for max min.
The max min SI, right? Well, you can pick any arbitrary value of P here, and then also compute the minimum power solution using these beamformers. Of course, beamformers are not matched with the resulting power, right? You can do it iteratively as well. I don't know if it converges.
But I think if like the users are experiencing almost the same channels, then
yeah, you don't lose much. And that's actually what you will see in the homework. In the homework, you are asked to compare as a function of P, what is the max min rate or max min SINR common, what is the minimum, what is the maximum common SINR that can be satisfied for all users given a power constraint. And you will be asked to plot both unnormalized and normalized. Then you look at the normalized case where any the gamma normalized by the gamma optimal from using these beamformers. This is the optimal. Right. For fixed SINR, that's the optimal. And then bisection, you can find the maximum SINR given the power constraint. And then you're asked to compare that to the zero forcing, match filter, and the heuristic solution, right? So all these the the beamformers you can compute at once, right? Match filter is just matched to the channels, normalized. Zero forcing also normalized, just zero inverse, and then the heuristic, just assigning here, you have normalized beamformer there, and then you just bisect over that 5-4 formula, right?
Yeah, but in this is equal power allocation to all users, right?
It's not in the downlink. The downlink power allocation can be different.
But this is downlink.
Now this is the compute the normalized beamformer, right? This is the normalized UK, right?
Oh, yes.
Still, to compute the actual downlink beamformer, you have to solve the power p. You have to multiply that with the square root of pk, right? And that you find for fixed SINR. You can, for example, if you want to implement the bisection to find the maximum SINR, this doesn't depend on the SINR, it just depends on the p, right? So you compute this, you get the normalized beamformer U, okay? Then you go to 5.4 here. So your G matrix is fixed, its U's are fixed. What you will be changing is this gamma, okay? Now you start from certain gamma value. You set the minimum, let's say 0, maximum, whatever, 100. And then you start in the middle, 50. You try 50 here. Invert the matrix. Compute the sum. If that sum is much higher than your allowed power, you will decrease the SIN, right? Note that this can be also infeasible, meaning that if, especially when you apply match filter there, when you invert, when the SIN target is too high, you plug in this DA in here, invert, compute the P, some of the terms can be negative, which is the sign for infeasibility, right? Meaning that gamma is too high.
Using this, shouldn't some of the P be equal to the initial P we assigned?
No, here, because we have now just fixed the U. Of course, in the end, they will be the same, because in the bisection algorithm, you will find a solution gamma where the sum of P equals the original P, right? In the end, they hold, but not in the process. Okay. Does this make sense? So in your feasibility check, in the bisection algorithm, you have to check both options, whether the power is above your target power, or some of the powers are negative. If powers are negative, it means that SINR cannot be satisfied, right? So you have to decrease the SINR, okay? The two conditions for feasibility. If the sum power is higher than capital P, or any entry in P is negative, then decrease, okay? For the other way, if now sum of P is less than, okay, sum of P is less, but okay, for both cases, you have to put the condition that all P has to be positive, okay? That's the first condition. Okay, but anyways, you can implement it. Very straightforward, if else structure. While loop and then if else. Okay. So this is a quite intuitive and very simple regularized zero forcing. It's used a lot in practice. Right? In practice, they suffice in most cases. You don't have to compute compute these optimal lambdas, or by using the heuristic, the loss with respect to the optimal in many cases is minor, right? And this is actually demonstrated. This is from the here some Emil's signal processing magazine tutorial paper. With two scenarios, 4 antennas, 12 antennas, 4 users. Okay. Here we are computing the average sum rate, average over multiple channel realizations. The sum rate, sum of log 1 plus SINS over all 4 users. So we know this function here. This function here is concave, but when we make this SINR variable, the SINR constraints are not convex, right? And they have to be approximated. So there's no globally, there's no single solution for global optimality. You can do kind of a reduced exhaustive search of branch and bound. This curve here is basically computed using this branch and bound method. You can see some details in this paper, how they are computed. Kind of reduced and well constrained, well-defined way to carry out an exhaustive search and reduced exhaustive search. Okay. So, but for this one, we can claim optimality. Right? It's exponentially complex when the size of the problem increases. Right. So now we have zero pausing, match filtering, then we have the optimal, and then the regularized zero pausing. You can see that regularized zero pausing is optimal asymptotically equals match filter, and that goes to the zero pausing, obviously, the highest in R. And match filter, because you don't try to handle the interference at all, becomes interference limited, and that's why it has a maximum rate that can be supported. You can see the average sum rate here is a bit more than 5, meaning that the rate per user is 1.2, 1.25, meaning that the SINR per user is close to 1, a bit more than 1. Okay. You can see that you don't lose much relatively. Okay, here, maybe somewhere here, relatively you lose the most, but still not much with respect to the optimal. And but this is for the sum rate. In your homework, you are asked to plot similar, but for the maximum SI. The objective is, what is also one question. Okay. The objective is one gamma 1 gamma k. We want to maximize minimum over k. Okay, maximize the minimum rate, and obviously, since we have this is the bijective mapping, you can equivalent to maximize max min gamma, right? Because in the end, the rate will be the same for all users. The SINR will be the same, so it's the same that. Maximizing the common SINR is the same as maximizing the common rate. Okay? And this is what you asked to do. What's similar? Now, if we have a much more degrees of freedom than the users, the difference is zero. less. Even zero forcing works fine, right? Because we have such a large null space available. Null space is 8 here, right? So we get a lot of beamforming gain there.
So how do we choose among this space?
But
Here. How they have used among this 8, for example, null vectors?
well, we use directly the
Power allocation, something?
to be honest, I'm not sure what they have done. Of course, equal power loading is here as asymptotically optimal, right? When you go to the highest enough. So you can use simply H. This is your zero forcing, right? This is the same as, you know, in wireless communication 2, we have this projection. We have this projection matrix. Let's not get there. Anyway, this one uses the available null space optimally, right? The match filter sense. It's a match filter in the null space. Okay. Of course, when we have a square matrix here, null space is 1. So basically, meaning that the space for that we don't have any degrees of freedom for match filtering in the null space. Okay. Maybe you have to go to the discussion of the wireless communication to recall this. Okay. So depending on the system setup, the difference in between different approaches is minimal. In the massive MIMO case, the number of antennas becomes large with respect to the number of users. Match filter is asymptotically optimal, right? So these are single cell results. In multi-cell, it's less straightforward, right? Because in multi-cell, you should also take into account the users that are served by other base stations, right? You should try to avoid causing too much interference to other cell users as well. So for that you will be using degrees of freedom. Imagine that we have 12 antennas, but we have 4 cells. Each cell is serving 4 users, right? So you have a scenario where, let's say, you have 12 antennas here, 12 antennas here, 12 antennas here. This guy is serving 4 users. Okay. In a single cell setup, zero forcing would work fine. This one here, also serving 4 users. 4 users. Okay. But now, if we just design the beamformers based on a single cell, we are ignoring the interference. Okay. And this interference can be significant if the users are close to the cell edge, for example. So we have to also assign some dimensions. Basically, in the inverse, you should also take into account these channels and these channels into account. And now, if you want to have zero forcing solution, the null space is 1 again, right? Zero forcing would work quite badly in the lower center. Okay. Then the optimal design will provide you much more gain again. We will get back to this in the next slide. Okay, so this is the heuristic case. Now something completely different. Still minimum power beamforming, but assuming some of these that the channels are corrupted. So we have base station serving users. Okay, we could assume just for fun a scenario where each user kind of FTG scenario, which actually matches quite well with the error model that we introduced here. That each user measures the downlink channel, it quantizes it with certain number of bits, right? It quantizes each, if the channel vector is, H1 here, is H11, H12, and so forth. So for each INQ, each INQ you assign some number of bits, say 6 bits or 3 bits or whatsoever, and report back to the base station. You have some quantization noise, right? So that quantization noise, what the base station receives is the quantized version or estimated channel, H tilde K. But the actual channel HK is something different, right? So this difference between HK and HK tilde can be modeled by this additional error term UK, which is unknown to the transmitter because it does not know the actual level, right? You have some quantization happening, all these values are rounded to this value, all these values are rounded to that value, right? So the actual value is not known. The base station in this case would just know these quantized levels, right? But this fine information is unknown. For that, we would need to have much higher granularity, okay? Infinite granularity, asymptotically. So this variation here is now modeled with this corruption. And actually for this type of quantized feedback, the noise can be bounded, right? It's quite evident that this variation here is bounded, right? For this quantization level, the actual level can be anywhere between these two bounds. Okay, so it's bounded noise. Okay. In general, if you assume like TDD case, using least square estimator, it's limited power. The noise introduced at the channel estimate can be considered to be Gaussian. Right? So it's not bounded, it has tails. In principle, infinite tails. Right? If you bound it, you cut the distribution. Okay? You cannot guarantee anything. Right? Only probability. Here we have a model where the error terms are bounded by an ellipsoid or sphere. Like if E is diagonal matrix, this is a ball, n sub t dimensional ball. Okay, 2 antennas circle. Okay, 3 antennas, 3-dimensional ball, 4-dimensional ball cannot be drawn, and so forth. So now we have an error model for a estimated channel at the base station. H tilde is the known channel, the estimate of feedback model, the feedback from users, and the UK is now the unknown part, which is unknown, but it's known to be bounded by a certain shape, right? It's bounded by this ellipsoid. And the size of the ellipsoid is controlled by the size and shape of the ellipsoid is controlled by this E matrix, right? So the E, basically the the eigenvalues of this E matrix is the shape. Right? If the eigenvalues are equal, it's the ball. If they're different, then it's a an ellipsoid, multidimensional ellipsoid, and so forth. Can be anything, depending on that. Right? Can be also a line when, for example, the size is 2 and then 1 eigenvalue is 0, right? There's only uncertainty along this line. Okay, so now if we have the model, noise is bounded by this pair. And then making this eigenvalues large means that this mu has to be small to satisfy the constraint. Right? So if this E can be control the accuracy of the feedback. The more feedback bits, the larger the value, the eigenvalues of E, and vice versa. Okay, so worst case optimization problem. So this is the real channel, right? HK. It's just replacing now the HK in the original formulation with the new channel, which consists of the known channel and the unknown component. Okay, just directly replacing. We are still minimizing the power subject to SI constraints, such that for each user, the unknown part is contained in this convex set defined by the ellipsoid, right? That U can be any point in the circle, right? If we project this to 2D, so this constraint has to hold for any realization of U bounded by this circle, right? This is the new constraint. If we have to, we want to find a minimum power such that SINR is satisfied given these beamformers for any possible realization of noise inside this known uncertainty region. Okay. So far, so good. So this cannot be reformulated as an SOCP. I'm not going to draw it, but the thing is that because there's this unknown part, we cannot assume that the product is real, right? We cannot get rid of the absolute value. We cannot assume that HK tilde UK times WK is always real because UK is unknown, okay? Always. It simply cannot be assumed to be real value. Okay. So what we can do is we reformulate them via SCR. So we are following here exactly the same steps as before. Defining a transmit covariance matrix WK, which can be thought to be outer product of these two, the beamformer, and the same some property holds. And we can write the SINR, you know, this is a WK Hermitian. This is exactly equivalent to the SINR constraint, the previous slide. Now we have actually convex problem here. For any point, we have a convex problem that holds for any point in U, right? So imagine U is fixed to be any point in this set. This is a linear linear expression, right? It's an STP for all possible points of UK. The problem here is that instead, in the noise-free case where we had just capital K constraints, now we have how many constraints? Well, infinite number of constraints, right? Because it should hold for any point inside its continuous ellipsoid, multidimensional ellipsoid. Okay, so it cannot be solved. Of course, we could solve it approximately by sampling. Right? This is actually something you could try to do in practice. You could, for example, just sample the outermost points, but you cannot guarantee still anything.
Even if it is like limited numbers, for each realization we will have different beamformer, right? Then how we should guarantee?
Now the thing is that this beamformer should hold. The single beamformer should hold for all constraints, infinite number of constraints.
No, I mean, if it is finite, like 10 realization only for that UK.
Yes, then it holds for these 10 realizations. Then we can
Ah,
guarantee that it holds for those 10 realizations, but we have no guarantee that it will hold for the other realizations. Okay, but it can work. Okay, if you add, for example, a little slack for the SI now on top, statistically it's good, very fine. Okay, this is convex but intractable problem. How we can solve this is using so-called S procedure. Let's go through that S procedure just for fun. I need to open the link here. No. This is quite detailed. So S procedure, mathematical result that gives conditions under which a particular quadratic inequality. So we have quadratic inequalities here, right? Is a consequence of another quadratic inequality. So this is the main thing here. So basically we have a quadratic inequality here. So x, imagine x is now the u vector. So satisfying this leads to satisfying this. Okay, satisfying the noise constraint leads to satisfying the SI constraint. Okay, let's see how we can plug in these values. Might take some time. So let me just start and we can continue tomorrow. Let me write this. Rather write this x p. This is for real actually, but it can be extended to complex. 2 times g 1 t x plus 1 imposes the other quadratic. Okay, and the end result lambda G1 could be another good homework for that. The final. Okay, so we can write this. So we have these 2 quadratic inequality. So they like for this if this holds, right? So this is the kind of line of thoughts. So these two quadratic inequalities can be written, the details are skipped, as a single STP constraint, right? So there has to be a lambda. This lambda is now also variable. So we can basically collect these terms from here and write it as a single STP. Two matrices here, difference of matrices. You can, if you are interested in, this is more like hardcore convex optimization. If you're interested in details, let's go to Void or any of these references. I just want to show that how this can be applied. It's quite straightforward, plug and play. How we can apply the S procedure to this the channel uncertainty problem. Okay. So let's see. So let's call this matrix here as AK. Okay. Just so that we don't have to rewrite it every time. So we are interested in this constraint here. We have quadratic inequality here. So UK UK minus 1 is smaller than 0, right? This is a quadratic inequality. Like this one, right? We don't have the second term here, right? Only the first term. As in UK is X. And then we have another quadratic, which we have to actually now expand. So assuming this is AK, so we have just, let's start just expanding. HK tilde AK, HK tilde. Okay. AK is 1 over comma target WK minus, all these terms here. This is the matrix A sub K. So the first term, corresponds to this times this times this, okay? And then the cross terms, we have UK permission, AK, HK, plus HK permission, AK, UK, plus UK permission, AK, UK. Okay. So now we can rewrite. So let's say this is UK. This corresponds to the first term, like UK equals X. Okay. Then we have the second term. Okay, now we are in the complex. These are real, but we can actually write this term here as 2 times real of HK permission AK UK. This term here you can consider to be equivalent to G. This is a vector here, right? This is the row vector. So that would be G2. Okay, plus a constant term. This is known term, right? HK tilde is known, AK is known. Well, this bunch of stuff that should be handled. Okay, so now we have that one minus n0, right? Okay, we have equality. So this should be larger than n0, or larger than 0, right? Because gamma can be taken the other side. So it's other way around. So this would be larger than 0. If you want to make it smaller than 0, it just reverse the signs. Okay. So now we just plug in these values in here. So we get lambda times f1, that is e k, lambda k actually. Now we have to have a for each, because we have capital K constants here. So we have e k, and we have 0, 0, and minus 1. Okay. Then we have minus a k. We have minus a k. Then we take the remission of this. It's a k remission hk, and here we have with the minus as well, minus hk remission hk, and then the constants minus hk tilde okay. So we can write it in a single matrix, ak plus lambda k ek ak remission hk. Then we have hk remission hk. And finally, we have hk tilde remission hk tilde minus n0 minus 1. Lambda k, that's good one. Minus lambda k. Okay. So let me check if I wrote this actually yesterday. It's correct. Yes. So now you can plug in these constraints in here. Replace this with that for each user, and you have an SDP. And the WK, the result is guaranteed to satisfy the SINA constraint for each possible realization of WK. Okay. The problem is that the WK actually for small uncertainty, the solution is almost guaranteed to be rank 1. It's actually a good problem to study. But then when the noise increases, then also the rank of WK increases. Okay. Now, if you want, in general, it's not so clear what to do if you have, like optimally, if you have a high rank transient covariance matrix. But if you want to find a rank 1 beamformer, what you can do is randomization. So now this WK is the transient covariance matrix. So you generate a WK from complex Gaussian distribution, zero mean WK covariance, right? And now you draw, so basically you generate IID vector and then multiply it with that square root inverse of WK, right? That's square root of WK. And then you generate 100 of those and choose the best. But then for that beamformer, the SINR does not hold necessarily, but you have to scale it. You have to scale it up. You just multiply it with
Overloading.
yeah, you should multiply that with some extra power. That actually will lead to some power loss. Okay. If you have a rank 1 solution, that's optimal. You can claim optimality. Rank 1 solution, optimal solution. High rank solution, not optimal. Okay. All right, let's take a break and continue tomorrow.